Okay, now let's get started. So, still fighting with the technology a little bit. Okay, there are some online, so I have the online students online too, so I'm going to review the test. And it'll be available to everybody right after this class online, and it'll last till midnight tonight. So I'm going to go over pretty much what's going to be on the test. I'll do it on this little thing here, and hopefully that'll work. And yeah. Still anybody? Oh, we're gonna do both like from there. There's zeros. Zeros and the other. Oh, I do. This true. All right, we'll make that work. Okay, so here big overview. So there's going to be there'll be some general questions. Then there'll be a number of questions to refer to figures, and I think all total, I think there's 8 figures. Okay, so one of the figures involves a design problem. Okay. Now, a couple of things about design problems. So let's say, oh my God, we have to fix the mirror image. All right, there we go. Oh, okay. This one. No, wrong way. What? All right, so, oh yeah, that's good. That'll work. Maybe I'll push this way just a little bit. All right, not too bad. Okay, so there'll be a design problem. So I'm going to come back and talk about these, and then there's one of the figures talks about math stuff. So you need to be able, and you can use your calculator, but remember your calculator is not going to help you with fractional portions in all probability. So anyway, so you need to be able to convert from decimal to binary and hex, and then the other direction as well. And then you need to do a multiplication and a subtraction, and then a change to 2's complement. So the thing about these math problems is, I should have written small. And let's see, we have an eraser somewhere. So, all right. So on the math problems, the only one that should give any you may have issues with is the 2's complement. Remember in 2's complement that we have to make sure the values fit. Otherwise, we're basically getting overflows and wrong results. And so remember in 8 bits, we can go from minus 256 to plus 255. No, that's wrong. We can go from minus 128 to plus 127. Because in 8 bits, we can go from 0 to 255, right? So we have 256 things, and we divide them in half. And 256 equals 2 to the n, or n in this case would be 8 bits. So n 2 to the 8. All right, so keep that in mind. That's the critical thing. So normally I'm going to ask you, I'm going to tell you how many bits to put your 2's complement value in. Pay attention to that. If you don't do that, if you just convert it to 2's complement, and then if you just convert the decimal to binary and then convert it to 2's complement, you'll make a mistake if the number doesn't fit, and it might not fit in, say, the 6 bits it converts to or something. So remember, make sure you put the number in the number of bits I tell you to do. All right. So that's the math stuff, and that's really the only tricky thing there. And then there'll be a proof with a truth table. So remember, all you have to show in the truth table is that the left-hand side, and you should usually build it up column by column, that the left-hand side equals the right-hand side for every possible value for all the variables, but the variables can only take on 0 or 1. So if you have 3 variables, that's only 8 possible combinations of values for the variables. And so that's easy to show in a truth table, that all 8 combinations result in the same value for the left side as the right side. Okay, so that's the idea of the truth table. And you just have to pay attention. So maybe we'll work a little problem like that or something. All right, write 2 possible midterm expressions and simplify for a truth table that has a don't care. Okay, so basically there'll be a problem for the don't care. Now, in the case of a don't care, so somebody tell me, when you have a don't care, how do you have to work that? How does that work? Well, yeah, go ahead.
You choose whether it's 1 or 0 based on what makes it simpler to solve.
So you have to look at what expression you'll get if you take the don't care to be a 0, which would mean if you're doing the midterm expression, you wouldn't include it. And then you have to look at what your expression would be if you took it to be a 1, which means you would include it. And then you simplify those 2 expressions independently and see which one simplifies the least complicated logic expression. And that gives you a pretty good idea of whether you should take the don't care to be a 1 or a 0. And that way you get a simpler expression if you choose correctly than if you choose incorrectly. And I suppose there are cases where it doesn't even matter, but most cases it does make a difference, and maybe all cases it makes a difference, I think. So anyway, yeah, so you can use the don't care. Well, there are cases where it doesn't make a difference. So anyway, so you have to basically solve your truth table 2 ways and pick the least. Yeah, okay. And then so that's that. And then I'll give you a little schematic of a network. I may have a bunch of input OR gates and an output AND gate. So that would be POS, or I might give you a bunch of input AND gates and 1 output OR gate. And that would be SOP. And you should be able to, if I label these inputs, you should be able to write the SOP expression, or if I put them into that, you should be able to write the POS, the SOP expression. So whichever it is. Remember, the POS has input OR gates, the SOP has input AND gates. All right. And then there are just a few questions about the difference between ASCII values, fonts, other codes like gray codes, codes that have binary value, like a binary representation. There are other, we call those weighted codes. You can do different weightings. The standard binary weighting, let's see if it's still on, yeah. So if you have like a 4-bit binary code, the high order bit is worth 8, 4, 2, and 1. So the low order bit, so if you write 1, 0, 1, 1, or 1, 0, so that's going to be 8, no 4, plus a 2, no 1. So it's going to be 8 plus 2. So that's going to count for 10. Or in decimal, we write 10. In hex, we write 0xa. All right. So you should know about weighted codes. You can weight the codes differently, obviously, but I'm not gonna really ask you about that. You should just know that if you have a weighted code, you can compute with it. Yeah, go ahead.
For hex, what, like, the 0x, like, what does that mean?
So the 0x is just syntax. It's just most compilers and assemblers these days will take 0x to mean hex. There are some other ones. Back in the day when we used one of the Motorola chips, Motorola used to use the $sign for hex. Just their convention. That's kind of fallen by the wayside. You don't see that much anymore. There were some other ways people wrote it, but you just don't see that anymore. So mostly everybody goes 0x as the syntax. And often for binary, they'll do 0b. So, and usually decimal is the default radix. So if you write a number and you don't specify whether it's binary or hex, it's assumed to be decimal in most cases. That's a fair statement. And that's what we'll do in this class. So if I don't write 0x, or if it's not obviously a binary number, a lot of times I'll just write the number. I won't write 0b, but because it's all ones and zeros, you'll figure out it's binary. Okay, and then fine. So let's see the dump here. Get that right. Oh yeah, and then there'll be and then we'll have a part of a 4-bit adder. So we will have the 4-bit adder. So remember, we've talked about this. The 4-bit adder has 4 bits of A, 4 bits of B. It has a carry in and a carry out and 4 bits of sum. So it has 9 inputs, 5 outputs, which means if you did the whole truth table, it'd be 512 lines. But we're only going to give you a couple of lines, and you have to be able to compute, what the output ought to be for that particular row. So I'll give you the independent variables, the A, the B, and the carry in, and you have to be able to figure out what the sum and the carry out should be for that row. And all you have to do is add the A to the B plus carry in as a least significant digit, and that'll tell you. So for instance, if your A is 1101 and your B is 1001 and the carry in is a 1, then your equation would be 1001 plus 1101 plus 1, and you'd add that up. 1 plus 1 plus 1 is 1, carry the 1, 1, 1, 0, 1. So the carry out would be a 1, and you have 0, 1, 1, 1 for the 4 bits of sum. Okay. So that's easy to do. And then you should know that if we want to turn that adder into a subtractor, you have to invert one of the inputs. Say we're going to subtract B from A. So you would invert all the bits of B, all 4 bits with inverters, and then you would add a 1 into the carry in, because that's how you make a 2's complement, right? You invert every bit and add 1. So that would give you the 2's complement. Okay. And of course, you have to make sure it's going to fit in 4 bits. And again, in 4 bits, you can go down to -8 and up to +7 in 4 bits. All right. Okay. And then I will also give you I'll give you a gate with a truth table, and you'll have to figure out you'll have to write the truth table for that gate. And typically, I'm going to use an AND gate or an OR gate. So what's important about AND and OR gates? Well, you should remember, if you have an OR gate, the unique output for an OR gate is 0. So if you have any inputs of 1, and maybe you've got inverters on some of the inputs. So if you have an inverter on an input, let's say you have an OR gate here. Okay. Let's say you have an OR gate here. And let's say you have an inverter on maybe you have, say, A, B, C, maybe D even. All right. So if you have 4 inputs and you have an output F, the only way you get a 0 for F is if all 4 inputs are a 0. But since the A is inverted, you have to put in A prime. You have to put in A to get A prime, or A has to be 1, so it's a 0 here after the inverter. B has to be 0, so that would be B prime. C had to be 0, so that'd be C prime, D has to be D prime, but the A would have to be non-prime in order to put a 1 in to get a 0 out. That would give you, and let's say here, say it's an OR gate, so that would give you a 0 out of the OR gate. Or maybe we put a bubble here, so that gives you a 1. So if it's a NOR gate, the unique output's a 1. Any other input is going to give you a 0 out because it's going to be a 1 before the bubble and a 0 after the bubble. So you have to figure out your unique situation and then figure out the other ones. And it's, pretty straightforward. It's just a little confusing. In an AND gate, it's just the opposite, right? In AND gate, all the inputs have to be 1 to get a 1 out. So if you have an AND gate, the unique output from an AND gate would be a 1, where all the inputs are 1s. So A, B, C. On the other hand, if you put an inverter here, then you'd have to have your unique output then is going to be a 0, and all the other outputs would give you a 1. Okay. All right, so kind of keep that in mind. That's pretty straightforward. But it just means you have to understand how an AND gate and an OR gate work. Okay, and that's it. That's what's going to be on the test, plus a few general questions. And some of the general questions will be SOP to POS conversions, but they'll be real straightforward. Okay, remember when you do, let's talk about these one at a time. So the design problem. So when we talk about a design problem, what we want to do is we want to make sure typically that we have the ability to store all the information we need. And usually that means if we have, let's say we want to store 1,000 things. Okay, well, so how many bits do you need to store 1,000 things? Well, you could take the base 2 log of 1,000 and round it up to the nearest integer. But most of you don't know how to take base 2 logs, including me. Although you can find a base 2 log calculator and do it. But an easier way is just to memorize the powers of 2. And it turns out there's a really easy way to memorize the powers of 2. The first 9, or you should almost already know, but because they go, well, if you start with 0, it's 1, but 2 to the 1 is 2. So 1 bit gives you 2 things. And then if you have 2 bits, you can represent 4 things. 3 bits, 8. 4 bits, 16. 5 bits, 32. 6 bits, 64. 7 bits, 128. And 8 bits, 256. 9 bits gives you double this, or 512. So you have to kind of know that one. And 10 bits is really easy. 10 bits is just 1K. 20 bits is 1 meg. 30 bits is 1 gig. 40 bits is 1 T. And after that, who cares? It's pretty big numbers. But 50 bits, I think it's 1 exabyte or petabyte. I always get those mixed up. I think it's exabyte and then petabyte. Whatever. So we'll say 50 is 1 E and 60 is 1 B, 1 petabyte. All right, those are really crazy numbers. Probably you can always look those up if you need to. So then, what if you need 4K? Well, if you need 4K, you need 10 bits plus 4 more plus. So this is. You need 10 bits plus 2 more, and that's 4K. Or what if you need 64K? Then you need 10 bits plus 6, you need 16 bits. What if you need half a meg? Well, or 512K, then you need 10 bits plus 9, you need 19 bits. And if you have 20 bits, you have a meg. And it figures 1 bit less than 20 would give you half of a meg, and 1 bit more than 20 gives you 2 megs. And 2 bits more, 4 megs, and so forth. So between every one of these decades, you just can count 2, 4, 8, 16, 32, 64, 128, 256, 512. And so what if you had to represent 26 million things? How many bits would you need? Well, you'd start with 20 for 1 million, Now I need 26. Well, then that 16 is too small. 32 is bigger, but you have to round up. So you need 25 bits. See how easy that is? You should just memorize this. You'll use it the rest of your career. You should know this really off the top of your head, or you can calculate it in your mind right off the bat. And then just remember, 10 bits a K, 20 a meg, 30 a gig, 40 a T. How tough is that? Pretty straightforward, right? You should know that. So if I say you need 1,000 things, then you need at least how many bits for that? That's right, you gotta have 10. That might be a little tight, so you're thinking you're gonna put in a little pad because the customer's thing might grow, and if you got 24 more people, you'd be in trouble. So you'd say, let's do 11 bits just for safety, or maybe even 12. Because 12 is a nice round number. So you'd probably do something like that. You'd make an engineering decision, and that's what you guys are gonna do. You're engineers, you make engineering decisions. Non-engineers don't make engineering decisions because they don't understand that you might want to leave a little headroom or whatever. Well, they probably understand that, but they wouldn't know how to do it. All right. So anyway, so if you have 1,000 things, the minimum number is 10 bits. What if I said you had 700 things? How many bits do you need for that? You need 10. 512 won't do it. Right? So you should just, knowing this simple thing up here, which you should have really in your head already, just knowing that, you can immediately tell me how many bits you need for whatever you're going to store, all the way up to trillions of things, which is a lot. Unless you're calculating the national budget, then you need more than that. Well, I don't know. I guess we're only up to what, 31 trillion? I guess that. So how many bits do we need to hold the entire national debt if it's 31 trillion? How many bits would that be? So a K is 10, a meg is 20, a gig is 30. So a tera is 40. So we need 40, and then we need 31. So we need at least 32. So that's 5 bits, right? So we need, so what did I say, 10? I have to think of it. So let's see. So it's a K, a meg, a gig, and that's a billion, and a tera, yeah. So we need 10, 20, 30, 40, 45 bits to get 32 trillion. So our national debt, we need at least 45 bits to keep track of it and growing. All right. Okay, the math, I think I already covered this. Really, let's look at a 2's complement number. So let's say I wanted to take say 53 and turn it into a 2's complement. You can use your calculator and figure out what the binary is. That's fine. I'll do it by hand. I'll probably mess it up. So I know it should be 26, right? Hopefully. So remainder 1, 2 into 26 is 13, remainder 0. 2 into 13 is 6, remainder 1. 2 into 6 is 3, remainder 0. 2 into 3 is 1, remainder 1. 2 into 1 is 0, remainder 1. And we're done. All right, so the number is going to be 1, 0, 1, 0, 1, 1. And I'm going to check it because that's what I do. So I know this is 1, 2, 4, 8, 16, 32. So 4 and 16 is 20, that's 52 plus 1 equals 53. All right, so 53, that's good. Oh, I erased it. What the hell? 1, 1, 0. What was it? 0, 1. 0, 1, 0, 1. Is that it? Yeah. 2, 4, 16, 32. Yeah. Okay. Okay. So yeah. All right. So now I want to switch that to a 2's complement. Well, will this number fit as a 2's complement value in 6 bits? Well, what will fit into 6 bits? So 6 bits is minus 32 to plus 31. Is this in that range? It's because it equals 53, right? No, it won't fit. So what happens if you just mindlessly do the conversion? Okay, so you copy bits, you get the first one, copy that, and flip all the rest. 1, 0, 1, 0, 0. Now you get a positive number. You supposedly have minus 53. Obviously, that's not because it's got a 0 there. So you're already in trouble. So what you have to do is you have to pad that sucker out. And I'll usually tell you, I want it in, say, 10 bits or 8 bits or 12 bits. So you pad it out to 8 if that's what I want. And now you flip it. And now you get 1, 1, 0, 1, 0, 0, 1, 1. Now that is a negative number and that is a positive. That equals positive 53. And this equals negative 53. Because in 8 bits, you can do minus 128 to plus 127. So because you get 256 things. Yeah.
You're not inverting the rightmost one because it's 2's complement, right?
Yeah, it's a 2's complement, right? There's 2 ways to do 2's complement. Flip every bit and add 1. Or start on the right-hand side, copy bits till you get to the first one, copy that, and flip every other bit. And if you do that, you get this. If you flip all the bits, so we'll flip them 0, 1, 0, 1, 0, 0, 1, 1, and then you add 1, you still get this. But it turns out flipping every bit and adding 1 is how the machine does it. But copying bits, starting on the right, copying bits, so you get the first one, copy that, flip every other bit. That's how you do it as a human. It's an easier rule to follow because you don't have to do the addition. In this case, the addition was easy, but sometimes it's hard because there are a lot of carries. Not hard, but tedious. All right. Okay, so you have to make sure those fit. And obviously, in 6 bits, it does not fit, but in 8 bits, it's fine. All right, so you just have to kind of keep your wits about you. All right, so that pretty much is the math. Remember, when you do the subtraction, if you're doing like 11.101 and you're subtracting, say, 10.111 from that. So 1 from 1 is 0, 1 from 0, you can't do it. So you borrow a 2, 1 from 2 is 1, 1 from 0, can't do it. So you borrow a 2, 1 from 2 is 1. And then 0 from 0 is 0, 1 from 1 is 0, and 1. And then you save the decimal point. So just if you have to do a couple of digits over, where you have to borrow, borrow this one. So you put a 2 here, and then you borrow 1 from that, and then you have a 2 over here, but you've got a 1 left there. So use 2's. It's much easier. Remember, you're doing the math in decimal in your head. You don't do math in any other base because you've never learned how to do it. You don't know the multiplication facts. You don't know the division facts. You don't do math in other bases because you don't know how. And you spend a lot of time in grade school learning how to do the math, including all the fractions and all that. Okay. All right. So that's pretty much the math stuff. So the truth table. So let's take the multiplying and factoring. So x, y plus x prime z equals the quantity x plus z times the quantity x prime plus y. All right. So let's prove this. Well, so we have 3 variables, x, y, z. And then we have and then over here, so you just create columns for all these. So we'll create a column for x, y. All right. So this is x and with y. There's a little and there. So you have to have 2 1s to get a 1 here, otherwise you get a 0. So clearly, all these are going to be 0 because x is 0 for the first 4 rows. Now x is 1 for these, so now you just have to look at y. Y is 0 for these 2, so 2 more zeros and then 2 1s. All right, and then x prime z. Well, now it's just the opposite. These will be 1s and these will be 0s because it's x prime and not x. And so we know the bottom 4 are going to be 0s. We don't even have to think about it. So these are going to be 1s. So what's z? It's 0 here, 1 here, 0 here, 1 here. So that works. And then x plus y. So you can do these x plus y. I'm sorry, x plus z, and then x prime plus y. So you just have to think. So if either x or z are 1s, that's going to give you a 1. Well, you know the bottom 4 are 1s, so you can go ahead and do those because x is a 1. And then here, only where z is a 1. So it's 0, 1, 0, 1. And here you have x prime, so we have 1, 2, 3, 4, and then only for y, so that's going to be 0, 0, 1, 1. And now you just do the left side and the right side. So the left side is just it's just these ORed. So you OR these, so you just need 1, 1. So that's going to be 0, 1, 0, 1. See 0, 0, 1, 0, 1, 0, 0, 1. And then this is going to be, these have to be both of them. So that's going to be 0, 1, 0, 1, 0, 0, 1, 1. And it turns out they do match for all possible values, all combinations of x, y, and z, all possible values of all combinations of x, y, and z. Both sides are equal. So it proves it's true. Now you can also do it with switching algebra, but we're going to do a little truth table. All right, so that takes care of that. And then the don't care. This may be a little bit tricky. And what's really interesting is you'll see how helpful the K-maps are, because they just do this for you. But let's say, so we have ABC and we have an output. So okay, and so here's our F. So let's say we have a don't care here, and then we have say 1, 1, 1, 0, 0, 0, 0. Okay, so let's write the expression. So there are two expressions we can write. We can choose this to be, we can pretend that's a 1, or well, first we'll pretend it's a 0, and we'll write that expression, and then we'll pretend it's a 1, and we'll write that expression. So if we pretend it's a 0, we don't use that term. So where the x equals 0, that'll be a prime b prime c plus a prime b c prime plus a prime bc. All right. And then we write it again, f, where f equals 1. So we're going to have the additional term of a prime b prime c prime plus all these again, a prime b prime c plus a prime b c prime plus a prime b c. Now we try and simplify. We always use the theorem x y plus x y prime equals x. So we're trying to combine these things. So we can combine these two because we're only differ by a single variable, and that gives us a prime b prime. And we can combine these two, and that gives us a prime b. And now we have a prime b prime and a prime b. We can combine those two and get a prime. Here we can combine these two, or let's see, can we? No. We can combine these two and we can get a prime b, the c prime and the c, that drops because it changes. Here we can't really combine this with this one, but we can combine it with this one. So we can get here a prime, the b drop, a prime c. And now we're done. We can't really do anything else because these two can't combine. So our answer then is a prime c plus a prime b, or just a prime. Which one's simpler? Where we choose x, the don't care is a 1. You see how that works? Yeah, go ahead.
So is that the only, the chart you gave us about the conversion?
Yeah, that's the only theorem you can use in this case. Yes. Yeah, it turns out that's the only one you need. When you're simplifying your min-term expressions or your maximum expressions, this or its dual, the dual is just x plus y quantity times x plus y prime equals x.
The dual is the only. What would you say on the test, the dual, that the xy plus x prime would be the only one we need?
Yeah, this is for anytime you simplify a truth table directly, you pretty much only need this, or if you're going to do the POS form, the max terms, then you would need the quantity x plus y times the quantity x plus y prime equals x. It's just the dual of this one. I mean, they're really the same. They're the same line. It's S1. You only use S1 for this. I think that's a fair statement. Well, maybe one exception would be if they're all ones, then you know the output's one. You don't even have to write the expression. Okay, so now what would happen if I had, instead of what I had there, let's say I had 2 don't cares and a few ones here and the rest were zeros. How many expressions would I have to write to figure out the best way to choose those? That's right. You have to write 4 expressions. And if you had 3 don't cares, it's out of control, right? Now you got to write 8. So that the K-map, on the other hand, lets you look at it immediately and just say, oh, yeah, no. So in this case, the little truth table would look, the K-map would look like this. You do X, X, 1, 1, 1, 0, 0, 1. And you go, well, you get that whole column, and then you get these 2. So you would choose these 2, and you choose both of those as ones.
Maps a little bit.
Yeah, we're gonna start those on Monday.
The only thing I don't understand is the diagonals when they're on the edges.
Yeah, we'll explain that. Don't worry about it for this test. Okay, how we doing? Good, we got time. Okay, so that's that. And then the 4-bit adder. So the 4-bit adder looks scary, but it isn't. So let's talk about that. And then I'll give the DOF-FOP conversion. Okay, so 4-bit adder. So here's our thing. Remember, we make that 4-bit adder by using the technique of design by iteration, right? Somebody tell me what design by iteration means.
A few pieces and then stick those pieces together.
Exactly. And the only issue when you do design by iteration, you have to figure out what information flows from module to module and which direction it flows. And I suppose it's possible it could flow both ways, but typically it flows one way or the other. When you have a comparator, and we use comparators all the time. When you have a comparator, what happens is you compare the higher order bits first. So let's say we have 2 numbers. A equals, say, 1, 0, 0, 1, and B equals 0, 1, 1, 1. So which one of these numbers is bigger? A is bigger. When you actually build the hardware to do this, the first thing you do is compare A3 to B3. And if A3 is bigger than B3, you're done. Because you don't care what the other bits are, it doesn't make any difference. It'll never make B bigger than A. So in a comparator, the information flows from the higher order bit to the lower order bit. When you add 2 things, let's say we add these, the carries flow this way, right? So you always have to keep in mind which way the information flows. Now, I'm not gonna pimp you much more than that. I don't even think I asked that question. But so in this case, our 4-bit comparator, what we have is we have 1, 2, 3, 4, 5, 6, 7, 8, 9 inputs. That's our carry in. So we have A3, A2, I'll just write the A. So we have A3, A2, A1, A0, B3, B2, B1, and B0. And up here we have 1, 2, 3, 4 coming out. Some 0, some 1, some 2, and some 3. And then you have a carry out. Carry out. Okay, so 5 outputs, 9 inputs. So if say our row is for A, B, and a carry in, if we have say 0, 1, 1, 0, 1, 0, 0, 1, and 1, and then we want our carry out and our sum 3, sum 2, sum 1, and sum 0. So what's this line going to give us? Well, all we have to do is add this A to this B plus the carry in is low order. So we'll write 0, 1, 1, 0 plus 1, 0, 0, 1 plus 1. So 1 plus 1 is 0 carry the 1, 0 carry the 1, 0 carry the 1, and 1 plus 1 is 0 carry the 1. So it's going to be 1, 0, 0, 0, 0. Which would be 16. So this is 6, and this is 9. No, adding that up. Oh, plus 1, 10. So 16. Yeah. Got to carry in. All right. So that's how that works. Okay, so easy peasy. All right, so let's see, some of the general questions. So, so let me just, I'll try and remember as many as I can, but, so we've talked about, designing for target hardware, right? When you design for target hardware, what hardware, what type of hardware, let's say, what are the types of hardware? Well, you can design for programmable logic. And that would be these days an FPGA or maybe a CPLD for a small project. So that would be one. Or you could, for a custom IC. And then we kind of divide those into two. And I don't even know, I don't know if people have totally agreed on the names for these. But one of them is a partial main IC, and you put on the last layer. And the other is just from scratch. So if you use this one, it's certainly cheaper because you only have to design one layer and the other parts already built. And what your one layer is, it connects all the other stuff. It's kind of like programming an FPGA, but it's done permanently. And because it's done with an additional layer, there's no big interconnect matrix involved. There's no bit file that has to get stored in memory. So you don't have to have the memory elements. You don't have to have the big interconnect matrix. And so you have a much more, a smaller part, and your timing, your clock pathways are very predictable with this compared to the FPGA. And in the FPGA, you don't really know how everything's going to get routed. So there's a lot of uncertainty because the synthesizer does all that for you. And so as a result, you have a little bit of control over it, but not much. And so you can have some real uncertainty in how the clock line's gonna run, and it can cause timing problems when you're trying to push the limits. So if you're trying to push the timing limits, it makes sense to think more about this metal, putting the metallized layer on an IC that already has a bunch of functionality built in, and then you just hook it up to get what you want, as opposed to generating a bit file to hook up all the programmable modules to get what you want. In this case, if you go from scratch, then you have total control over everything and you can get exactly what you want, but at a much higher level of cost. So where do you think you might want to use a custom IC? Like make one from scratch? Well, first of all, if you're going to make zillions of them, you don't want to buy expensive chips and program them. You want to make the chips yourself and try and keep the cost as low as possible. So number that you're going to produce has a big role in this. If you're going to make hundreds of thousands, you're probably going to make your own chip. If you're just going to do maybe a 300, then this would be very expensive. You'd really absolutely want to go the FPGA route. In every case I can think of anyway. And then where you have to have real control over the timing, but you're maybe not going to do that many, you might go this route as opposed to the FPGA. So if you're going to design for an FPGA, you need to know exactly what that target architecture looks like, and you probably don't need to simplify your expressions all that much because you're using a lot of lookup tables or essentially read-only memories where you're just going to put the whole truth table straight into the chip. You're not going to, for every little piece you design, you may have a truth table and a state table, and you can just put them straight in. So there are a lot of reasons why that target hardware. On the other hand, if you're going to make a brand new integrated circuit from scratch, you want to simplify your equations as much as possible because you don't want to have to put in a big ROM if you don't need it. If you can get by with a few equations, a few gates. So you'd obviously want to simplify as much as possible and see anywhere you can squeeze savings, because the smaller you make that little die, the less it costs you to produce it, because you get all wafers are basically roughly the same size. I guess you can get them different sizes, but they come in some pretty standard sizes because they grow these big silicon crystals of silicon dioxide, and then they slice them into wafers. And so your wafers are pretty much all going to be the same size. So if you shrink your surface area, you can put more of those circuits on that same wafer. And so it's gonna cost you the same amount of money to process that wafer. For every single wafer you process, it's gonna cost you the same amount. So if you have 300 circuits on it, you're gonna divide that cost by 300. If you only have 200 circuits, you're gonna divide that cost by 200. That's a big difference, yeah.
So, how many questions are we looking at?
They're 48. Yeah.
Right, and the time limit is what, an hour and 30 minutes, 2 hours?
I'm giving you 100 minutes. So that's, it's a little over, it's not quite 2 hours. It's 20 minutes short of 2 hours. That should be gobs of time. You won't be, now, what you don't have time to do is to do original research from scratch on the internet for every question. That, that's not gonna, you're probably not gonna get through 48 questions like that in 100 minutes. You've got a little over 2 minutes a question.
It's gonna be on Blackboard or it's gonna be through your book?
No, it's on Blackboard. Yeah. The way the questions will be presented, they'll be randomized. So everybody will see the questions in a totally different order. So you'll have, that's why it's a little bit of a pain, because they'll refer to different figures and they'll jump around because you won't get all the questions for figure 1 and all the questions for figure 2. And then there are a bunch of general questions. But every question will be randomly ordered. And then you have to answer that question. Once you go past that question, you cannot go back to it. And you only get to see one question at a time. Now, I know everybody would like to see the whole test, but it just invites intellectual dishonesty problems. So that's why we don't do that.
And is it, fill in the blank, multiple choice, how does that work?
It's all machine gradable. So there's questions where there's a single selection out of a bunch, where there's multiple selections out of a bunch. There's true and false, and there's some where you have to put a number in. If you have to put a number in, I'll tell you, don't put commas, don't add additional numbers, just put in the numbers you absolutely need. I usually give the instructions that make that straightforward.
If you go back in and look at it as well, like let's say we did add a comma by mistake, but we're used to it, would you go in and?
Yeah, I've had, so a couple things happen. Sometimes students will say, I think question 5 is wrong, and I'll go look at it. And if it's wrong, I'll probably take the test myself this afternoon sometime. Here's what's really great. So you guys take the test and you say you took it, started at noon, you finished, at 1:30 or whatever. When your 100 minutes expires, it automatically uploads. So make sure you're done at 100 minutes. And then when you're finished, you can upload it yourself, but it'll automatically upload at 100 minutes. If you're doing it and you go someplace where your internet's not likely to get it disrupted. So don't go to some, photo thing out in, East Jerusalem, hoping that the internet will stay up in 2 hours. That'll get you into trouble.
But Professor, what did they say they'll help me as long as I give it my credit card?
Looks like an A to me.
Don't go to Ukraine.
Don't go to Eastern Ukraine.
I feel like the schools are. Oh, yeah, the Elon Musk Starlink.
I gave this to my security number. He didn't give me the answer. I'm doing this to you. I don't understand what I hear wrong.
They also have $50 billion.
Or, they have,